So today we are going to learn about constant velocity and average velocity. So here we go. All right, so the easiest way to do this is to just kind of dig in and do an example, all right? So what we've got going on here is we have got our friend Roy, whom you will get to know very well this year, and he is going to run 90 yards up the football field and 30 yards back down. So because I'm kind of going sideways here, I'm going to do this. I'm going to call this way up, and I'm going to call this way down. As you will learn in a minute, direction in physics is actually super important. All right, so my drawing is this. My dude's going to start here, and he's going to run 90 yards this way. And then from there, he's going to turn around and he's going to come back 30 yards this way. Oops. Try that again. Boop, boop. Sorry, just getting used to this new software here. All right, so there's my drawing. I find that drawing a path that making a drawing that represents the path that the object followed is often useful. All right, so what we're going to do now is we're going to calculate the distance that our dude Roy here just ran. Oh, notice, by the way, this whole trip took him, we should do this. The whole trip took him 15 seconds. So let's make a note. T equals 15 seconds. That may be useful later on. Okay, so what distance did Roy run? Well, distance is exactly what you'd think it is. It measures the length of the path that the object followed, right? So Roy went 90 meters this way, and then he turned around and came 30 meters back. At the end of the day, he's going to say, I am tired because I ran 90 yards, and then I ran another 30 yards, which gives us 120 yards, which is how far he ran. All right, so there we go. Now, another quantity that we are often interested in is what's called displacement. Notice the symbol for displacement is a little triangle followed by the letter x. It is, so in chemistry, hopefully you learned that the triangle means change in. X, we'll learn a little bit later in the video, is position. So that's why there's two symbols there. So that triangle x means displacement. And what this does is it measures the length and direction of the line from an object's initial location to its final location. So on my drawing here, here's my dude's initial location. And then he ran 90 yards forward, 30 yards back, and he ended up here at this final location. So my displacement is the length and direction of the arrow that points from initial location to ending location. All right, so let's not worry about the direction quite yet. It's up the field, right? So he ended some distance up the field. How far? Well, he ran 90 up the field and then came back 30 for a net gain of 60 yards, right? So that's my displacement there. So the displacement is going to be 90 yards up minus the 30 yards he came back. So we end up with 60 yards. Okay, so there you go. That's displacement. All right, and we'll get back to this direction thing in just a minute. Okay, all right, so, all right, now, in algebra, one of the things that you hopefully learned is that distance equals rate times time, right? In physics, we call that rate speed, or in a minute, we'll see we call it velocity, right? So if distance is speed times time, if we algebra this, we could solve for s and discover that our speed is the distance divided by the time. So in the case of Roy, we just finished doing this. We discovered that Roy ran 120 yards along the field. And then hopefully you remember that our time was 15 seconds. So that means that the speed that he ran at is 120 divided by 15, which is, what is that, 8? That is, in fact, 8. Yeah, so that's 8 yards per second, right? Now, to be clear, that's a little bit, so that's the speed that he ran. But think about it. If you're running 120 yards on the football field, you're not going to run the same speed the whole time, are you? All we know is he ran a total of 120 yards in 15 seconds. So this actually gives us what's called his average speed. So this is our first physics equation, which we'll almost never use this year. Average speed is distance divided by time. Okay? Average speed. Shlabam. Okay? So there we go. So that's his average speed. He averaged 8 yards every second. Okay? Now, in physics, we use a slightly different equation. So instead of doing distance equals rate times time, we do displacement equals velocity times time, okay? Or velocity is displacement per unit time, okay? So keep in mind here, so for velocity, think about what happened. So our dude ran, what did he do? He ran, sorry, my drawing's getting a little bit cluttered here, isn't it? So he ran 90 yards this way, right? And then he turned around and came 30 yards back. You know, let's just redraw it. So what did he do? He ran 90 yards this way and then came back 30 yards. But in the end, he was only 60 yards from where he started, right? So his displacement is 60 yards, and that took him 15 seconds. So he averaged only 4 yards per second, right? So this is what we call his average velocity. All right, and the symbol for it is, let me clean up my board here a little bit to get myself some more room. This is his V average. So this is our second new equation this year. Boop, 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 boop. Boop. Average velocity is displacement over time. Average velocity. So again, he wasn't running 4 yards a second the whole time. In fact, he probably was running faster than that because he had to backtrack, right? So our average velocity is 4 yards per second. This means that he averaged 4 yards up the field every second, okay? So now we have to go back and dig into this whole positives and negatives thing, the whole direction thing, right? So a minute ago, I commented that distance was the length and direction of the line from an object's initial location to its final location. So how do we deal with direction? Okay, this is a really, 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 really important concept in physics, all right? So here we go. All right, so in physics, we often care about the size, we call that the magnitude of a quantity, and the direction. All right, so a lot of the concepts that we talk about this year in physics are called scalars, and a lot of them are called vectors. All right, a scalar is what, like, pretty much every number that you've ever talked about in your life up until right now has been a scalar because it just measures magnitude or quantity. All right, so here's a list of scalars down here. The distance that you drove to school today, that's a scalar. You just drove some number of miles to get to school, right? Speed. Oh, I was going 25 miles per hour. That tells you how many miles you went every hour, right? It's kind of just like counting the number of miles you go per hour, right? Mass, you could measure mass, you know, oh, the mass of this bottle of Coke is whatever, 300 grams, right? Time, oh, well, that took me 15 seconds, right? You're just counting quantity. Later on this year, we'll talk about energy. Volume is a capital letter V. I don't know why I put that one on there. We almost never use it. All right, so these are all scalars. They simply measure just quantity or just magnitude. You're literally just counting a thing. All right, now these other quantities over here in red are called vectors. So these measure both magnitude, they measure quantity, and they measure direction. Okay, so in that last example, Roy's displacement was, what was it, 40 yards, I think? 60 yards? What was it? 60 yards, right? His displacement was 60 yards. What was the direction? Up the field, as opposed to down the field, right? Now, what is up the field? Well, we'd have to see the field and agree which way is up the field and which way is down the field, but it's implying direction, right? So the symbol for displacement is a little triangle and an X, but when we write it, we put what's called a vector hat over it. That's why I said they wear hats, okay? So anytime a quantity is a vector, it wears a little vector hat, and it basically looks like a little arrow that goes over the thing, all right? And what that arrow says is, hey, direction matters, okay? The direction that this thing points matters. So this displacement points 60 yards up the field as opposed to down the field, right? I guess I should say up the field as opposed to down the field, right? Velocity, similarly, when you're driving down the street, if I say, what's your speed? You can say 25 miles an hour. If I say, what's your velocity? I want to know the direction. So you're going to say 25 miles an hour north or south or along Mac toward St. Clair Shores or whatever it is, right? Force, we'll learn later on about force. This is a vector quantity, so we put a little arrow over it. Acceleration, vector quantity, little arrow over it. Momentum, symbol for momentum is a lowercase letter p. Put an arrow over it, all right? So all those little arrows over our things tell us that this thing is measuring both quantity and direction. Okay, so there's a couple of ways to talk about direction. All right, one way to do it is to just describe it in words like I've been doing, right? Up the field, down the field, north, south, east, west, left, right, up, down, right? Now, a lot of times we can take a shortcut. So it turns out if our motion is linear, in other words, so that the motion takes place along a fixed linear path, and not when you say linear, I don't want you to think in a straight line. In physics, linear just means that there are two possible directions of motion. Okay, so when you throw a ball straight up into the air, there are two possible directions. It can go up or it can go down. All right, once you've established what those two directions are, we pick one of those directions to be positive and the other one to be negative. And which one is which doesn't really matter. Usually, if I'm doing up and down, I usually make up positive and down negative, but not always, right? Like if the thing's always moving down and it never goes up, then let's just make down positive, right? It just sort of depends on the problem. But the point is, for each individual problem, if there are two directions for motion, you're going to pick one of those directions to be positive and the other one to be negative, okay? All right, car driving on the street. Oh, it doesn't tell me which way the street runs. Okay, cool. Let's just go forwards is positive, backwards is negative. A roller coaster, same thing. The roller coaster can go either forwards on the track or backwards on the track. So forwards is positive, backwards is negative. Kid on a swing, you can swing forwards or backwards. Forwards is positive, backwards is negative. Kid on a merry-go-round is a dumb example. I wish I hadn't put it on here. Pulley system, so suppose we've got like a thing like this. So here's the edge of a table with a little pulley on it. I've got a block here, and a string runs around the pulley and then down. All right, well, so this thing could move. I'm going to grab a different color because my thing's getting cluttered. Either forwards and down or backwards and up, right? Those are the only two directions the system can go, right? Either this guy wins and it goes forwards, or, I don't know, maybe there's a squirrel or something pulling this way and it goes the other way, right? So there's two directions it can go, positive, negative. Or maybe you don't like that. Maybe you want to do it the other way. I don't care. You just got to be consistent with it. So that way, once you get your answer, you know what the positive means or what the negative means, all right? So if there are two possible directions of motion, one of them's positive, the other one's negative, all right? And that's basically what this says right here, all right? Now, I will, as I sort of alluded to, in most problems I use math conventions, which means if it's about up and down, then up is positive, down is negative. If it's about left, right, forwards, backwards, I do positive, negative, usually. As you will see as we get further into the year, I sometimes make exceptions on that. All right? Now, quick word about units. Distance and displacement. Remember, these both measure how far your object has gone, right? And as a result, the units that we would use to measure either of these would be units of length, units of distance. So we could do yards, we could do inches, we could do feet, we could do miles, we could do kilometers, we could do meters, we could do centimeters, we could do light years, right? We could measure in number 2 pencils, right? This desk is 47 number 2 pencils long, or whatever. That'd be a long desk, all right? So those are our units for distance. Time, well, that's going to be in seconds or minutes or hours or days or weeks or whatever, right? And then speed, remember, speed is distance over time. And velocity is displacement over time. So both speed, oops, sorry, I wanted that to be a different color. So both speed and velocity, oh my goodness, speed and velocity are going to be measured in units of, oops, oh my gosh, why are these colors not cooperating? Sorry, I'm just getting used to this tablet here, and apparently my aim is bad. There we go. So speed and velocity are going to be measured in one of these units per one of these units. So you can measure speed in yards per second, oops, or in, I don't know, miles per day, or in kilometers per minute, or in centimeters per year, right? Okay. we will usually, and when we get a little bit further into this class, we're pretty much going to stick to metrics. So we're going to usually use standard units are going to be meters for distances, seconds for time, and then so our velocity and speed are going to be in meters per second. All right? Okay, so let's dig a little bit deeper here. All right, now, so suppose Roy drives his scooter east at 5 miles a minute for 6 minutes, and then he turns around and goes west 15 miles at 3 miles per minute. We're trying to find the average speed for the whole trip. All right, so again, I think a drawing is a good problem-solving strategy. All right, so let's do this. There are 2 parts to the trip. So let's do the first part of the trip in red. How about? He goes east at 5 miles a minute for 6 minutes. So first part. Let's see, he went 5 miles a minute. So that's his velocity. Notice it tells me the direction. So let's go ahead and do this. Let's make east positive and west negative. So his velocity for the first part of his trip is 5 miles per minute. I'm going to put an arrow over that because it's direction, right? The time is going to be 6 minutes. All right, and then there's a second part of the trip where he goes west at 15 miles, or goes west 15 miles. So the second part of his trip, let's see, 15 miles. That's telling me how far he went. Let's go ahead and put a direction on it. He went back 15 miles, right? Oh, and it's telling us the velocity he went at, 3 miles per minute. But again, he was going west, so that's going to be negative, right? All right, and what we're trying to do is we are trying to find his average speed for the whole trip. V average equals what? Now, please be careful. Please stick to the equations that I give you in class. A lot of times students look at this and they go, okay, well, he's going 5 miles a minute here, 3 miles a minute here. The average of 5 and 3 is 4. So the average speed is 4 miles a minute. And that turns out not to be right. We have to stick to the equations. All right, so we are, oh, I just lied, didn't I? We're not looking for average velocity. I'm sorry. We're looking for average speed. My bad. On the next slide, we're going to do average velocity. All right, so what is average speed? It's distance over time. So I need to know the total distance that Roy drove and the time it took. So let's see. So for the second part of the trip, I know how far he went. He went 15 miles. The direction's negative, but remember, distance doesn't care about the direction. So I think I need to put this all together. So let's see. Let's figure this out. So if I go 5 miles per minute for 6 minutes, for this first part of the trip, my displacement is going to be velocity times time, right? I went sorry. Let's see. So I went, oh my goodness. Whoa. Sorry. So I went 5 miles per minute for 6 minutes. Oh, well, that's 30 miles, right? So that's the displacement for the first part of the trip. For the second part of the trip, I don't know how long it took. So I'm going to go, all right, let's see. Displacement is velocity times time. Now notice here my velocity, it seems like it's constant, right? Because for the red part and the blue part there, it doesn't say anything about him speeding up or slowing down, right? He's going 5 miles a minute for 6 minutes, right? And now he's going 15 miles at 3 miles per minute. So if we algebra this, we discover that the time is displacement over velocity. So he went negative 15 miles at negative 3 miles per minute. That's going to take 5 minutes, right? So now we can find his average speed for the whole trip. What distance did he go? Well, he went 30 miles and then another 15 miles, right? Notice the direction doesn't matter here, right? Distance is just the length of the path he followed. He went 30 meters and then another 15 meters. Miles. So that's 45 miles in. How much time did it take? Well, the first part of the trip took 6 minutes. Second part took 5 minutes. 6 plus 5 is 11 minutes. So divide this. I'm going to grab my calculator because I wasn't smart enough to do this in advance. And I'm going to type 45 divided by 11. And you get 4.09 miles per minute. And notice the average is a little bit higher than 4 because he spent more time going at a faster velocity, faster speed. Okay, so that's his average speed. You got to find the distance for the whole trip, divide it by the time for the whole trip. All right, so as I said before, now we're going to find the average velocity, and it's almost the exact same idea. So I'm going to do a thing that I used to hate it. I had a chemistry teacher when I was in high school, and he always did this, and it drove me bonkers. But I am going to cheat because otherwise this video is going to be 7 hours long. Whoop. Copy. Boop, 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 boop. Oh. Paste. All right, so, all right, now, oops. All right, so now, same thing. It's the exact same problem, but this time we're trying to find the average velocity for the whole trip. So again, a lot of these numbers are the same, right? Let me move this a little bit more. And you might want to maybe pause the video at this point and just like recopy this down, you know? Just take a second and do that. It might be time well spent. Let's see, how else can I fix this? Okay, good enough. Whoa. All right, so now what's the average velocity for the whole trip? So average velocity is displacement over time, right? So what's his displacement for the whole trip? Well, he went 30 miles east and then 15 miles west. So that's 30 miles east and then 15 miles west, and the whole thing again took 11 seconds. So it looks like he ended up going 15 miles east. Notice I know that it's east because my displacement ended up being positive 15, right? So his overall net gain, he went farther east than he did west. Sorry, he went farther east than he did west. And this took him 11 minutes. And so his average velocity is 15 divided by 11, 1.36 miles per minute. And notice it includes direction. So now I need to say what the direction is so that, you know, whoever's reading my work knows that he ended up going east overall. All right. Now, if we all agree that positive is east, then positive is sufficient. But if it's unclear which way is positive, you need to write it in words, okay? All right, so there we go. All right, so at this point, we've got two equations. Average speed is distance over time. Average velocity is displacement over time. When you write this velocity equation, try to remember those arrows. Notice if your speed and velocity are constant, then you can do this. All right, so this works if your speed is constant, i.e. if you're not speeding up or slowing down. And this one you can use if your velocity is constant. All right, if you don't speed up or slow down, then it's distance equals rate times time, just like you learned in algebra. All right, finally, we are so close to being done. Sometimes in physics, we need to describe not how far an object has gone, but where an object is, and we call that location or position. All right, and the symbol for position is a letter X. Displacement is change in position. Okay, so position's where you're at, displacement is how much that position changes. All right, so our textbook definition now of displacement is an object's change in position during some time interval. All right, and hopefully you remember from chemistry, anytime you're finding change in something, it's always final minus initial. So my change in position is final position minus initial position. Notice those arrows. These are vectors, so they should have arrows over them. Okay? So notice when you calculate displacement, this sort of shows you that it doesn't care about the path that you followed. All it cares about is where did you start and where did you end. All right, so to see this, let's do an example here on this last slide, and then I'll shut up and you can go have a bowl of ice cream or something. All right, so in this example, my dude is going to go from a position of -7. Oops, I wanted to color code this. He did this. Here we go, red, right? So my dude's going to go from a position of -7 to a position of +9. All right, so what's the displacement? Well, you could count. Let's see, he went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 kilometers, right? It's a long walk. Or you could say, well, he's got to go 7 kilometers to get to 0, and then another 9, so 7 plus 9 is 16. Or we can do change in position is final minus initial. So final position is 9, minus initial position was -7, minus negative becomes plus 16 kilometers. All right? Now in the blue chunk, he goes from a position of 9 back to a position of 3. Oh. Back to a position of, oh my goodness. Back to a position of 3. So now the displacement is final position minus initial position, and we get -6 kilometers. Notice the negative sign is telling me that he's moving towards the negative end of my number line. Okay? You could also think of it as his position is decreasing, right? Because he went from 9 down to -3. Now, what's the displacement for the whole trip? Well, let's see. So it's, oops, I wanted this to be a different color. So his displacement for the whole trip is his final position minus his initial position minus negative, so we get 10 kilometers, right? So let's see, he started at -7, ended up at 3, so that is, in fact, 10 kilometers. Darn it. That is, in fact, 10 kilometers in a positive direction. All right, so there we go. That is our first video. Now, one of these days I'll get editing software and I can shorten these, but right now I don't, so you just have to deal with it. All right, peace out.